Electron configurations are one of the methods that we use to show the arrangement of the electrons in an atom in their orbitals. I'd like to start by writing an electron configuration for nitrogen and dissecting it, or showing you what the numbers and letters mean in relationship to the quantum numbers we talked about in the quantum mechanical model. So nitrogen has the element symbol N. Its atomic number is 7, and so it has 7 protons and 7 electrons. Its electron configuration is 1s2, 2s2, 2p3. So if you're talking about or asked to write an electron configuration, that's what we're looking for, that's what it looks like. Now right now I don't want to worry about how I got this. Let's just think about what each of the numbers and letters mean. So the numbers in front of the letters, the 1 here, the 2, and the 2, these all are indicate the principal energy level. So remember, the principal energy level can have any number that starts with 1, and then it's a whole number. It goes 1, 2, 3, 4, 5, 6. On the periodic table, we really wouldn't have to go higher than the number of 7. And for this course, we really don't go much higher. There's a 4, possibly a 5. So here, that's the principal energy level. Then the second thing we notice here are the letters S and P. Now the S's and P's are indicate they're the sublevels. They indicate the sublevels, and recall that inside the sublevels there are the orbitals, and that's where it's the highest probability of finding the electrons are. So the S's and the P's contain the sublevel. Now depending on the sublevel, it will vary how many orbitals, and that means how many electrons. Recall that each orbital can only hold 2 electrons. That's the Pauli exclusion principle. So anything with an S, they can hold, the S sublevel holds 1 orbital inside of it, so that's a maximum of 2 electrons. So it would never have more than 2 in an S. The P sublevel has 3 orbitals inside of it, and so that would make a total of 6 electrons because each orbital can hold 2 electrons. The D sublevel contains 5 d orbitals, and so that can be a total of 10 electrons in that sublevel. And then the F contains 7 orbitals. Any type of orbital can only hold 2 electrons, so 7 times 2 gives us a total of 14 electrons. So the S's and the P's tell us what sublevel we're in. Now, the last number here are the little superscripts, the 2, and the 3, and this tells us the number of electrons that are in those particular sublevels. Now notice, if you look down here, the S can hold a maximum of 2, and both of our S's are completely full with 2 electrons in them. And then a P, it could hold a maximum of 6, but we don't need to put in 6 for nitrogen, we only need 3. You might say, why? But because we have 2 plus 2 plus 3, that equals the 7 electrons that are in nitrogen. So we only need to represent the electrons that are in the nitrogen. So that's the dissection of an electron configuration. Now let's see how we can relate those and find those numbers, the ones, the principal energy levels, the sublevels, and the number of electrons in relationship to the periodic table. So in effect, we'll be able to write the electron configuration for any of the elements. So here is an electron configuration, a periodic table that's from your textbook. And it's organized to help us write the electron configurations. So to figure out the energy level, we're really just going to refer to what period the element is in. For the representative elements, or anything with an A, the energy level represented, the principal energy level, will be the same as the period number. So if you notice down here, they have the same number in front of the sublevel as the energy level they're in. Now in the transition elements, the energy level drops down one. And here's why. As in any given principal energy level, it will always, the order is always the S sublevel first, followed by the P, then the D, and then the F. But however, the farther you get away from the nucleus, sometimes like energy level 3 overlaps with energy level 4, and so it will go, the electron goes back and forth between, the electrons as we fill them go back and forth between the third and the fourth level. Well, we can even take this into account on the periodic table. If you remember that when you're going through the transition elements, the energy level is 1 less than the period that you're in. And if you're down here at the inner transition elements, which we won't in this class, it goes down to 2 less. So looking at the periodic table, to do any of the electron configurations on the periodic table, we would not need an energy level higher than energy level 7. Now that answers part of it, so now we know how we would get the energy levels. That's the first number. But we also need to know how to get the sublevels, the S's, the P's, the D's, and the F's. And the periodic table is in blocks. And if you look down here, it's color-coded on this periodic table. The first two groups, 1A and 2A, represent the S block. So anytime I'm in there, I'm in the S's. The purple one over here, they're 3A through 8A. Those are the P's. The D's are represented here. And then the F's are down here. So now on the periodic table, we can figure out the energy level and we can figure out the sublevel. So now we would only need to know how many electrons go into each one. Well, each box on the periodic table represents 1 electron. So we're going to end up counting how many boxes that we go in. Now, I like to think of this as reading a paragraph. And when you read, if I were going to treat this like a paragraph and I wanted to read, I would start up here on the first block and I would read from left to right. And then when I was done with that, I'd go left to right. And I would keep going down the periodic table. Now, when I think about reading, the funny thing about it, or maybe the easy thing about it, it would be like reading the same paragraph over and over. So you're always starting up at the top of the paragraph and reading. The only difference is you'd be stopping at different places because we'll be stopping at the element that we want to find the electron configuration for. So let's go to nitrogen again. And I had it on the previous page. On this periodic table, nitrogen, it's in group 5A. It would be right here in this box. So we're going to start up here where I have this thing. And so look here, I'm in level 1. I'm in the first row. So I'd write 1. When I come in, I go into the S. And in the 1S, it's here. I'm going to count across. I put 1 electron in, 2 electrons in. So that's 1s2. Okay, I've finished the first row, so now I come down to the second row. Now I'm in the second energy level, and I start in the S's, and I count 1, 2. Now remember, S can only hold 2, so I couldn't ever have any more. But also as you go across here, look now, as I go across, I'm no longer in 2 S's, I'm in 2 P's. So I write down 2P, and then I go 1, oops, sorry. I go 1, 2, 3. And then I'm going to stop there because I get to nitrogen. And so that's how I get the electron configuration for nitrogen. I count it through. Now, one thing I didn't mention in the last one, and I want to mention now because it's important, is there's something called the valence shell. And this is the highest energy level. And so if I think my energy levels, I have 1, and then I have 2s, and 2 is the highest. So this right here is the valence shell. I'll just write it since I've written it over. These are the valence, this is the valence, and it has 2 plus 3, 5 valence electrons. Now the cool thing for anything with an A, if you notice nitrogen is in group 5A, and that's not a coincidence. For any of the representative elements, the group number tells us the number of valence electrons. So I would like to do I'd like to do 2 more on this particular thing, and then I have a couple more things to talk about with Lewis structures. Now I'm going to take an eraser. Let me erase this one. I don't have room. And I want to erase that stuff. Okay, so this time I would like to do the element right below nitrogen, which is phosphorus. So phosphorus is in 5A, and it is right here on the third level. So I'm going to start up here, and so I start in at 1s, and I go 1, 2. Then I go down, it's like reading, I go across, and then I'm going to come here, 2s. 2s, and I go 1, 2. Then I go across, you got to finish the whole row. Now I'm in 2p, 2p, and I go 1, 2, 3, 4, 5, 6. Remember, the p sublevel has 3 orbitals, so it can hold 6 electrons. It's all filled up. Then I come down to here, 3s, so I say 3s, and I go 1, 2. Then I keep going across, and now I'm in 3p's. I say 3p, go 1, 2, 3. Now the valence shell, I have levels 1. This is all level 2. And so then level 3 right there, this is my valence, and it has 5 electrons. Now the interesting thing, nitrogen's valence was 2s2, 2p3. So what you see is when elements are in the same group, they have the same number of valence electrons and basically the same configuration, just different energy levels. It's that same valence electron configuration in elements in a group that give similar chemical properties to those elements. So we expect elements in group 5A to have similar reactions because they have similar valence electron configurations. So it's important for those valence electrons. Okay, now I'm going to erase the phosphorus, and I would like to do one that goes down into the D's. So let me erase phosphorus. I know I'm erasing some other things, but you can go back and look at it if you want earlier in the video. Okay, so I'd like to do a transition metal, and I think I'd like to do nickel, which is right here. So we're going to start the same way. So I start up here. I'm on the first energy level. So it's 1s, and I count 1, 2. Then I go down to 2s, and I go 1, 2. Go across to 2p. 1, 2, 3, 4, 5, 6. If it's all the way across, you know in p's it's 6. Then 3s, remember s's can only have 2, 1, 2. Go all the way across, 3p, and notice we're starting the same way we have with the others. 1, 2, 3, 4, 5, 6. Then I come down to 4s. Oh, I might run out of room. I go 1, 2. No, I won't. Good. Then I go to 3d. I go 1, 2, 3, 4, 5, 6, 7, 8. Now you're like, wait, you went 4s and then 3d. Well, remember, the transition elements are 1 less in energy levels than the row that you're in. And so you get 1, this gives the transition elements kind of different chemistry because they have 2 levels that are not complete. So that's kind of cool. And the second thing is you see this overlap where you actually go into the 3rd level, then the next level is the 4th one in terms of energy, so it goes into the 4th and then into the 3D. If I had to, oftentimes in transition elements they don't talk about valence electrons, but because they have 2 shells that are incomplete. But if you had to, in terms of the definition, you would choose the 4s2 as the valence electrons because they're in the highest level. So you saw on that last one on nickel. So nickel was way down here. And I'll rewrite it real quick. Okay, it starts to get pretty long, and so there is an abbreviated electron configuration, and what they do is you can use a noble gas, so the noble gases are in 8A, and you put it in parentheses. So basically the noble gas in front of nickel, so it's this one in the 3rd level, and this one doesn't have any of the symbols on it, but it would be argon. So argon is the noble gas in the period in front of nickel. So instead, if we wrote out the configuration for argon, all of this right here is argon. So instead of writing all of that, in an abbreviated one, we would write argon in brackets. And then all we write are the electrons that are in the period that nickel's in. So we would say 4s2, 3d8. And so you can do that with, and the only one you can put in brackets, is a noble gases. So you can't put any element in there. It can only be the noble gas, and it's the one in the period before it. So let's say, for example, we'll go way down. Let's say I wanted to do way down here in period 5, and I wanted to do strontium, which is right here. If I had to start from the top and write every row, that would take a lot. But in the abbreviated form, you'd go to the noble gas that's in the row before it, which is period 4, and that's krypton. So then you would write, so for strontium, you would write in brackets krypton, which tells the person looking at it that up to krypton all the electrons are there. Then you would only write what's here. So this is 5, that's 5s. So you'd say 5s1, 2. 5s2. So in the abbreviated electron configurations, in parentheses, you write the noble gas and the period before it, and then you just write the configuration of the electrons that are in the period or row of the element that you're interested in. The other thing that, I didn't spell diagrams right. I'll fix it. There we go. The other thing that I want to mention is something called an orbital box diagram. And this is another method of writing electron configurations or showing how the electrons are arranged. If I go back up to one, let's say, I'll do carbon. Let's do one that's way up at the top. And carbon, if you look on your periodic table, is 1s2, 2s2, 2p2. Now this is the electron configuration right there. An orbital box diagram, in my mind, is like an illustration of that. So I think an S, remember an S has one orbital, so we would draw one box. And that box represents the orbital. I like to write one S underneath it, but a lot of times people don't. And so there's my 1s, there's the box, and then I look up here, there's 2 electrons, and we draw arrows as the electrons, and you draw one arrow going up and one arrow going down. Pauli exclusion principle not only tells us you have only 2 electrons maximum, it tells us that they have to have what's called opposite spin. So one goes up and one goes down. That's the fourth of the quantum numbers, is one electron has positive spin and one has negative. For us, remember, all we need to know is one arrow goes up and one arrow goes down. And so then 2s, since it's s, I would only draw one box because there's only one orbital, and so that has 2 electrons, so 1, 2. And then the p's, though, remember in the p sublevel there's 3 orbitals, so I would have to draw 3 boxes because each box, all of these represent the 2p sublevel. Now there's only 2 electrons, and there's another rule called Hund's rule. I call it a bus riding rule, but basically it means that when there's open seats, that goes into the open seats first before it pairs up. So if I had 2 electrons that I needed to put in those 3 boxes, I would put them in 2 empty boxes instead of pairing them up in 1. So if you had written it with, let me erase it and I'll write it incorrectly, then I'll rewrite it. So if you had written it like that, that would be incorrect. Okay, it's called Hund's rule. What we want to do, the correct way, would be to have 3 boxes, because it's a P, and go 1, 2. And these electrons there, they're called unpaired electrons because they don't have pairs. These here are called paired electrons. So let's try one. I don't like drawing the boxes, but let's try chlorine. So chlorine, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. That's an electron configuration. Its box diagram, okay, let's see. An s has 1 box because it has 1 orbital. So 1s, and it has 2 electrons. 1, 2. 2s, s only has 1 box because it only has 1 orbital. 2 electrons. Then p's right here, that's going to have 3 boxes because p's have 3 orbitals, so all of that is the 2 p's, and it has 6, so 1, 2, 3, 4, 5, 6. Then the 3s, and s only has 1 box because it has only 1 orbital, and then the p's again have 3, 1, 2, 3, and those are the 3 p's. We go 1, 2, my arrows don't look very good, 3, 4, 5, and that's it. There would be only 1 in this one, there wouldn't be 6. So these are what are called orbital box diagrams, or just box diagrams. And it's another way to represent the electron arrangement. Okay, so one other thing that I want to mention at the end of this is that there's 2 exceptions that are common in electron configurations, and they're in the D's, and it is chromium is 1, and anything below chromium, molybdenum, and tungsten. And chromium, if I was writing it, oh my goodness, sorry. Let me take that away. I don't know why I put that on there. Okay. So chromium, I'll write its abbreviated form. It's argon. Then it is 4s2. Now what you would think, okay, this is what you would expect, is 4s2 3d4. Okay, this is what you would expect. But here's the thing, to have a d orbital that's half filled, it can have 10. So to have it half filled is very stable. So what happens is one of these s's moves up. So 4s, you'd now have a 1, 3d5. And so what actually happens, what we see, is this one, okay? Not this one, even though it's what we would expect. So that is the same thing. Anybody that has 3d4, this would happen. So chromium, molybdenum underneath it, tungsten, all of those would have it. Now the other exception is also in the D's, and it's in the second to last column. And the example I would do is copper. And copper we would say AR, and we would expect 4s2 3d9. That's what we'd expect. But you might have a guess. Also, for the D's, half full is very stable, and completely full is very stable. And so in this case as well, it is to the advantage of the stability of the electrons for the S1 to be moved, that one of the S to be moved. So what we see is argon, all that's the same, but 4s1 3d10. So that is what we see, is this one and not this one. And the other ones that this would happen, we would also, anything under copper, so silver and gold, we would also expect this to happen. So these are two common exceptions for the filling of the electron configurations. Down in, when you go in the inner transition elements, in the F's and so, there's more exceptions, but we're not working with those. So I hope that you can see the relationship between the periodic table and electron configurations, and have fun doing electron configurations.